Hello, guys. Welcome to another episode of Cuda Education. So today we are moving along. So as promised, we're just doing high-level overviews of each of the steps. So there are 16 steps, going from a fresh new blank Xcode um, project, right? Mac OS Xcode, metal project with nothing in it, all the way to the modern renderer project, which is freely available. If you Google Apple Apple Metal sample library and search up model renderer, one word, modern renderer, one word, you will get the full project, which is like the scene of a bistro. Okay, so to go from a fresh, clean slate project, with nothing in it, all the way to the bistro scene, we have 16 steps. So this is step 8. And obviously previously we were at step 7. So step 8 is the depth prepass. So as promised, I'm just going to quickly and efficiently jump through all of the steps to 16, just so everyone has an idea of what the overall picture is and what we're doing. And then later on, once I get finish all of these high level overviews, I will go back and fill in the details of each of the steps and get into the weeds of things. But for right now, I just want to keep it concise, fun, entertaining, and give you guys an idea of the battles that we are facing, right? So this is step 8, depth prepass. Goal: eliminate overdraw by rendering depth first. Then use equal depth test for the main color pass. Only fragments at the winning depth run the expensive fragment shader. Textures plus blend fong. Okay, so we have gone over depth testing related stuff, both in Metal and also in Vulkan on the channel. We've actually, gone quite in depth in it. So the basic idea is, we have a scene, we have objects in the scene, we have a camera that looks on the scene, and basically what we're trying to do is figure out what objects are viewable by the camera and what objects aren't viewable by the camera. If the object isn't viewable by the camera, we skip over processing that object, right? So we're not going to be spending processing time, energy, effort, drawing things that are never going to be seen, right? So we need to eliminate things that are not seen from things that are seen, and that's what um, the depth test conversation is all about, right? So again, if we reread the goal, you will understand, have a better understanding of what we're eliminate overdraw by rendering depth first, then using equal depth test for the main color pass. Only fragments at the winning depth run the expensive fragment shader, textures plus being flong. Okay, so the equal depth test. So that's basically testing, you have two objects. Are they equal to each other in depth or are they not equal? And there are different algorithms, less than, more than, all of that stuff. But again, all we're trying to do is figure out what are we processing and what are we not processing. If it's something that's not going to be visually seen because it's obscured by an object in front of it, then we won't take time, energy, and effort processing that. So we have AAPL simple.metal, two files changed. Depth only vertex in, reads only position attribute, and then vertex depth only. Transforms position to clip space, returns float forward directly. No fragment shader needed. All right, so that's under the APL simple.metal. We have APL renderer.mm, new IVAR, depth only pipeline state, vertex only, fragment function nil equal nil, position only, vertex descriptor, no normals, UVs, no color attachment, depth right only. And then another new IVAR, depth equals state. MTL compare function equal, depth right enabled equals 0. I believe we we dabbled in this a bit in a previous series of videos, but we dabbled in this stuff. And then drawing MTK view restructured into two passes. Pass 1, depth prepass. Pipeline, we have a pipeline, depth only pipeline state, depth less and right on, binds position and camera params only, draws all opaque submeshes frustrum culled, populated depth buffer. Frustrum culled basically means, in sort of the zone or the view space of the camera, is it viewable or not? So if it's outside of that view space, it's culled. It's removed. Pass 2, main color. So mesh pipeline state, depth is equal plus right off, binds, normals, UVs, textures light, params, draws, all opaque submeshes, output lit, textured color 0 overdraw. Both passes share the same render encoder. Okay, what did not change? APL shader types.h, no new files added, lighting, materials, textures unchanged, APL mesh, APL camera. Build status 0. Should look identical to step 7. Same lighting, same textures. The benefit is performance. The fragment shader texture sample matting plus blink fog now runs exactly once per visible pixel instead of potentially multiple times due to overdraw, right? So again, it's only basically doing the stuff that's visibly on the screen and not anything other than that. Why this matters for later steps. Step 9, G buffer, expensive multi RT fragment writes benefit hugely from 0 overdraw. Step 13, AO, depth pyramid is built from this P-pass. And then step 16, ICB, GPU driven culling operates on the depth buffer from this P-pass. Yeah, and then we go to step 9. So visually, nothing changed in this step. So visually, nothing changed in this step from the previous, from step 7. So if we go here, we could see that basically we have the same image as we had before. So this is all behind the scenes stuff, but we're trying to make our algorithm more efficient. Maybe at some point I will run a graphics debugger kind of thing to see if there's a performance difference between step 7 and step 8. But that is for a later date, right? Right now we're just trying to hop, skip, and jump between all the steps and get to where we want to go for now. Anyway, this is Cuda Education, guys. Thank you for watching. Have a great day.